So our goal is to figure out a polynomial which has cosine values as its roots. And those cosine values must have the angle in arithmetic progression as well as it should be of certain format. So first of all, let's understand what the problem actually is. So if n is a whole number and r is some natural number and r is less than or equal to n, so r can be 1, 2, 3 till n, right? All of these values. R can be any of these. It's varying as we want. Then we define some quantities. First of all, we define this thing a sub r. It is e power I 2r pi upon 2n plus 1. So over here we have 2n plus 1, that is an odd number. So this thing only works when your cosine values are of this kind of format. So I did say that we are finding a polynomial which has cosine values as the roots, but instead of doing that, we will do something even better. We will find a polynomial which has two times of the cosine value as the root, because that helps in simplification. But essentially it's the same thing, right? You can just, instead of putting x, you can just put 2x in that polynomial, and then you will just have the polynomial that you actually want. So it's the same thing. So next we define this thing t sub k. So it's a polynomial in x such that t sub k of xr is equal to a sub r power k plus a sub r power negative k. So the thing is that a sub r power k and a sub r power negative k, the addition of this can be written as a polynomial in x sub r. Right, it's very much doable. So once you got that polynomial, just replace every x sub r with x, and that polynomial is what we are referring to as t sub k. Right. So just using this property that x sub r is basically just a sub r plus a sub r, but the inverse of that. So a sub r plus 1 upon a sub r. Using that property, you can just write this polynomial. You can write this expression as a polynomial function in x sub r. And of course, we'll not use x sub r for the actual polynomial definition. We'll use x. So right now we don't have the actual expression, but it's still a good definition as far as this thing is going. So it's clear, like it's very obvious that t sub 1 of x sub r, that is just x sub r, because you know Euler's theorem and all that stuff, right? Next, I'll call t sub k of x sub r as t sub k comma r. So that's just shorthand for t sub k of x sub r. It's still the same thing. Don't get confused by that. Right, and now we finally turn to our goal. So our goal is to figure out what this product, which is basically the polynomial, what this polynomial should be. So it's the product from r equal to 1 till n of x minus x sub r. So for example, if n was 3, then 2n plus 1, that would be 7. So we will be talking about 2 pi upon 7, 2 into 2 pi upon 7, 3 into 2 pi upon 7. Only 3 of these, because 1 till 3, that's 3 terms. So these would be the roots, or I should say zeros, of this polynomial. And of course, this is a monic polynomial with these as zeros, right? That's what we need to figure out. So here's all the derivation, but before doing that, I should first of all give you a picture of what we are looking at. So these things, f sub 1, f sub 2, f sub 3, these are the polynomials that we want to look at. So this thing, when you put n equal to 1 in this, you just get f sub 1 of x, which is 1 plus x. And this whole thing, so I'm just gonna, yeah, this looks better. So this thing, that is exactly what we are looking for. That's our goal. And this varies as n varies. And for some values of n, I've written out what the function looks like. So f sub 1 and f sub 2, these are actually easy to figure out because you can just figure out the roots themselves. Those aren't that hard. But after that, things start getting a little complicated when you go to f sub 3, f sub 4, f sub 5. So you want to generalize how to figure out what this polynomial is going to be. So you can see how this behaves. So this, okay, let's just put off all of these. Right, so you can see this purple line That's this polynomial, right? Our goal polynomial. And when I enable this, you see it changes color because basically this is happening. F sub 1 is basically overlapping with this line. Now that's for n equal to 1, for n equal to 2. We have this kind of thing. So that's good and all. But also for n equal to 3, this matches with what I drew. So you can see the color is not exactly purple because when I enable this, the red and purple match and it gets shaded like this, right? And same thing for n equal to 4 and 5, it perfectly matches. Okay, so let's go for the derivation now. So there's something that we do know. We know that these a sub r values, these are basically the complex roots of unity, so complex nth roots of unity. And now I'm going to exclude one from the roots and all the other n roots. It should not be n, sorry, it should be 2n roots because these are not the complex nth roots, these are the complex 2n plus 1 roots, right? So this thing to the power of 2n plus 1, that would be e power I 2r I, which is clearly 1. So these are the 2n plus 1 roots of unity, and we'll just look at n of these, not 2n plus 1 of these. So why am I doing that? Because sometimes there are two roots, actually most of the times there will be two roots that give us the same cosine values, and that's something that we don't want. And that's why we are only going to look at n of these roots. So the one in the first and second quadrant, those are the ones that we'll look at. Also we'll exclude pi. So if e power I pi that happens to be there, we'll exclude that, and that's why it's only till n. So 2n upon n, 2n plus 1, that can never be 1, right? It's going to be less than 1. So that's the last AR value that we'll look at. Correct. So the thing is that 1 plus AR squared till AR power 2n, that's going to be 0 because we know that this polynomial has 2n zeros. So we are not including x equal to 1 as a 0, and the other 2n zeros, we know those are there, right? And then we'll divide this polynomial by AR power n. Why am I doing that? I'm doing that because AR power negative n plus AR power n, that can give us a polynomial in AR plus 1 upon AR, and we know AR plus 1 upon AR is basically just 2 cosine of that angle, right? That's why we are doing this. So once you do this and you combine the terms, you basically get this thing. So you already know what t is, right? So t sub k, we define it like that. Cool. Now this is good and all, but it's not really easy to calculate what t is just based on these definitions and the fact that you can express it. Just because you can doesn't mean that it will be easy. So for actually doing it fast, we'll rely on this kind of recursion. So this recursion is very easy to prove. Just multiply t sub k minus 1 by t sub 1. And t sub 1 is basically what? It's just x sub r, right? Yes. So multiply that and you will immediately get t sub k plus t sub k minus 2, and then write this equation. So using this, you can always write t sub k as a polynomial, and that's like really easy, right? And then you can find out what this polynomial should be. But even that's not fast enough because you will have to in fact add up all of these small terms, and that's really inefficient. So instead we'll just define this whole thing as a new term. So we'll define s sub k sub r. Yes, I'm using r over here, but you get the thing that it's just a polynomial if you use just t sub k, right? And that's defined like this. So the left hand side of this equation, right, we know it's equal to 0 when you put x sub r in there, but otherwise it may or may not be 0. It's a generic polynomial, right? It's not a value. For this thing, this equation, it had a value on the left hand side. This s sub k is not a value, it's a polynomial, but s sub k comma r, that is a value. Hope you understand that. I did say that x sub r, just replace that by x, and that gives you polynomial. Yes, but okay, you should understand what I'm saying. Fine. So now we have defined this thing. How do we calculate this thing fast? Well, we use another recursion. So this recursion is very much the same thing as this recursion. And it's also not that hard to prove. Using this recursion, you can just use this definition and then get to that recursion. It's really easy. You just go from T2 all the way till Tk, and you use this recursion on each term from T2 to Tk, right? This recursion. And then once that's done, it will easily just boil down to this, right? And you already know what s sub 1 and s sub 2 is, because those are trivial. Those can be found out just by knowing the cosine values themselves. So that's not a problem. The real thing is that s sub 3, s sub 4, those things cannot be figured out just like that, because sometimes you don't know what the cosine value is, right? Okay, so s sub k is the polynomial. We already explained that, right? So it's the polynomial when you replace x sub r by x, right? In that expression. Fine. So it's clear that s sub n of x sub r, that's equal to 0, right? Because x sub r is clearly 0 for this thing, as you had this equation. So s sub n is a polynomial of nth degree. Why is that? Because of this recursion and because of the fact that s sub 1 has degree 1, s sub 2 has degree 2, and then this recursion basically ensures that degree is going to be n, right? So it's a polynomial of degree n, and it has roots, not roots, I should say 0. So 0 is x1, x2, x3 till xn, so exactly n zeros, right? All of these x sub r values that you have in our whole polynomial as zeros. It also has those exactly same zeros. And that's really nice. And moreover, it also has leading coefficient 1. Why is that? Of course, this recursion. It just keeps on going like that, right? So yeah, just got the polynomial, because this s sub n, this is a polynomial that has n roots, the exact n roots that we want, and it also has leading coefficient 1, and that means it's just this thing. So that's it, done. And how do we calculate? I mean, okay, you already know how to calculate this at this point, but still, let me just show you some examples of how to calculate it. So s sub k is equal to x s sub k minus 1 minus s subscript k minus 2. That's our recursion. We know what s1 and s2 are, so we can easily figure out what s3 is. It's just x times this thing, so x cubed plus x squared minus x, and then minus of x plus 1. So that's going to give us x cubed plus x squared minus x minus 2x and minus 1. And then you can go to s4 and s5 using the same recursion, right? It's much faster than figuring out all of these t1, t2, t3, 4 values and then adding them up. So this is the best method that we have for figuring out information about cosine values that you usually won't be able to figure out. So for example, I once got a question that what is secant of, well, what was it? It was 2 pi upon 7 plus secant of 4 pi upon 7. I think that's how it was, yes. Plus secant of 6 pi upon 7. So how would you figure out what this thing is? Well, you just use this s sub 3 polynomial. So we know that this thing is the same thing as, well, it's just a product from k equal to, or let's say r is equal to 1 till 3 of x minus 2 cosine of well, it's supposed to be 2 pi upon 2n plus 1, right? So 2 pi upon 7, 6 plus 1, 7, but then that times r, so 2 pi r upon 7, right? So yeah, these three numbers, those things, of course, like cosine of 2 pi upon 7, 2 times of that, of course, that thing is the polynomial, this polynomial, right? So that's equal to x cubed plus x squared minus 2x minus 1. Now we directly know that these quantities, these are the zeros of this polynomial. So for this polynomial, 1 upon x, so it's not a polynomial yet, we'll just have that polynomial later. So 1 upon x cubed and then 1 upon x squared minus 2 upon x minus 1 is equal to 0. For this equation, the zeros would just be 1 upon 2 cosine of 2 pi r upon 7, and that's just half secant of 2 pi r upon 7. And from here it's very clear. So yes, exactly. So you can see negative of negative 2 upon negative 1, that's just equal to negative 2. Negative 2 is the sum of our zeros, right, or the roots of this equation, and those are just these values added up. So basically this whole thing, call this thing, I don't know, call this thing capital M. So this will just be half of capital M. So capital M is in fact just negative 4, and that is in fact the answer that they give us. So yes, it's very useful, and in fact this is just like 1% of the actual power that this thing holds, because you also have these other terms, so you can figure out all of the things that you actually want, right? Everything. So we already discovered how to do these things for tan values, right? So for tangents and cotangents, we already figured out how to find polynomials that have those values as roots, right? So zeros. But for cosine and sine value, it gets a little complicated, because sine, it cannot be it cannot be written like in terms of cosine without using the square root. That's a bit of a problem, right? Because in that case you cannot find a polynomial that easily, and so you have to figure out a way that actually solves this. Yes, and doesn't cause that square root over there. So if you don't have that square root, like we did over here we never actually had square roots, or we didn't have to square anything, or yeah, nothing crazy, right? It's it's basically just a lot of calculation. And yeah, the sad thing is that there's no general there's no generalized closed form that you can directly use to figure out what these polynomials should be, and that's why you have to do all of this. You have to figure them out by hand, basically. So using this recursion and just calculation, just right. Okay, so that's it. That's all I wanted to tell you. That's the next video. And if you don't know what I was talking about when I said that we already know how to figure out polynomials for tangent roots, sorry, zeros, go check out some other videos of mine. Those explain it, right? So I'll see you guys in the next video. Goodbye.